Welcome back to Partial Differential Equations. I'm Dr. Jeff Groh. Today we're going to talk about PDEs in spherical coordinates. What do we mean by spherical coordinates? If we have here the usual XYZ coordinate frame, spherical coordinates allow for a radius which we will denote by a lowercase Roman letter r. It has a longitudinal angle which will be denoted by phi and a colatitude denoted by theta. Some of you may have seen these coordinates with the theta and phi exactly reversed. However, in most advanced applications, these coordinates are denoted as represented here. And so you may have to get used to thinking of these coordinates as phi being the longitude and theta is the colatitude. You'll recall latitude is the angle measured off of the xy plane, positive up, negative down. Colatitude is measured off of the North Pole. I'll let you check that the Laplacian of a function u expressed in spherical coordinates may be written as follows. The first term is two partial derivatives with respect to r. 2 over r times the partial derivative of u with respect to r. I'm going to write plus 1 over r squared times the quantity u theta theta plus the cotangent of theta times u theta plus the cosecant squared of theta times u phi phi. There are some alternative methods for checking these changes of coordinates, and I may give a lecture in the future about how to do that efficiently. For now, we're going to look at the steady state temperature problem, where we have the Laplacian equal to 0. We assume that r takes values in the interval from 0 to a. The colatitudinal angle goes from straight up to straight down, so it will take values between 0 and pi. And phi will take values between 0 and 2 pi. We assume, of course, that u is separable, and so we'll have functions r, which will depend upon the coordinate r, theta, which is a function of theta, and phi, which is a function of phi. We'll assume that the function phi is 2 pi periodic. Making the separability assumption, the equation turns into r double prime over r, of course, after we replace u with r theta phi and then divide both sides by r theta and phi as well, plus 2 over r prime over r, plus 1 over r squared times theta prime prime over theta, plus cotangent of theta times big theta prime over big theta, plus cosecant squared of theta times phi double prime over phi. To fully separate the variables, we need to eliminate this r squared. So we'll multiply both sides through by r squared. And then we can move all of these terms to the other side and then set this equal to some constant mu. Multiplying through by r and moving the term on the right over to join its terms, fellow terms on the left, we'll have r double prime, r squared times r double prime, plus 2r times r prime minus mu r equals 0. And we see right away that this is an Euler equidimensional equation. You can see that if we assume that r is of the form r over a to the n, we'll assume that n, for the moment, is a real number, then we get r double prime. Well, you see r prime is 1 over a, r over a to the n minus 1 times n. R prime prime will be n times n minus 1 over a squared, r over a to the power of n minus 2. Plugging that in the equation here, when we multiply r prime prime by r squared, we'll have an r squared over a squared. And so we'll pick up two more factors here. We'll have n times n minus 1 times r over a to the power of n, after accounting for that conversion, plus 2. Multiplying by r here, we have an extra factor of r over a. We'll have 2n times r over a to the power of n, minus mu times r over a to the power of n equals 0. We can cancel off the r over a to the power of n, and we obtain a curious equation, moving the mu to the other side. We'll have mu is n squared plus n. So you get a minus n here, plus 2n gives you n, or n times n plus 1, where n is a real number here. Let me write that out. Mu, in all cases, is n times n plus 1. We're assuming here that n is an element of the set of real numbers, so it's quite general. The rest of the differential equation becomes theta prime prime over theta plus cotangent theta, theta prime over theta, plus cosecant squared theta times phi prime prime over phi, and that's still equal to minus mu. So how do we separate the variables this time? We need to multiply by sine squared theta on both sides. We'll move this term to the left and this term to the right, accounting for multiplying by sine squared theta. We'll have sine squared theta, theta prime prime over theta, plus sine theta cosine theta, theta prime over theta, plus mu sine squared theta equals negative phi prime prime over phi, and we'll set this equal to some constant lambda. Recall phi is 2 pi periodic. It follows then that we should set lambda equals m squared. M will be an element of the set of integers. In that case, it's easy to come up with the representation for phi. In fact, I'm going to give you two representations for the function phi. The old one might be something like this: c1 cosine of m phi plus c2 sine of m phi. But there is a complex way to write this: phi equals e to the I m phi. Again, to get that 2 pi periodicity, lambda has to be m squared, where m is an integer. Using this complex representation, you'll recall the Euler formula, e to the I theta is cosine theta plus I sine theta, we'll have to do something about our inner products if a function has complex values. In addition, we have to do something with our solutions so that we come up with real valued answers. The only equation left over is sine squared theta, theta prime prime. We can multiply through by theta, I suppose, but we did have this over theta plus sine theta cosine theta, theta prime over theta, plus sine squared theta mu equals m squared. Multiplying through by theta and moving this term to the other side and dividing by sine squared theta, we have the following. Now this is something new. So we're going to need to work with this to turn it into something that we might recognize or something that we can otherwise solve. We're going to transform this equation by making a change of independent variable. We're going to suppose that s is cosine theta. These derivatives are derivatives with respect to theta. So we need a way to transform these old derivatives with respect to theta into new derivatives with respect to s. And so you can see that we'll have, by the chain rule, ds d theta here. Ds d theta is minus sine theta dds. So how about a second order derivative? Well, we'll have to take the derivative here with respect to theta, but we'll have to convert to derivatives with respect to s. Let's see, ds d theta we already know is negative sine theta. When we take the derivative here, we'll have to use a product rule. The derivative of the first term is going to be negative cosine theta times d theta ds, and it's still times this dds. And then we'll have to take the derivative of the second term. That's going to be negative sine theta times d squared ds squared. So when we distribute, we're going to have a sine squared theta d squared ds squared. This is 1 over negative sine theta, so we end up with 3 negatives. We end up with a minus. Sine over sine cancels. We have a cosine theta dds. How then does the differential equation transform? The theta prime prime becomes a sine squared times d squared theta ds squared minus cosine theta times d theta ds. That takes care of the first term. We have plus cotangent theta times theta prime, which we know to be minus sine theta d theta ds. And then we have plus mu minus m squared. This is cosecant squared. It's 1 over sine squared, which is 1 over 1 minus cosine squared theta times theta equals 0. Again, in making our conversion, sine squared is 1 minus cosine squared, and remember, s is cosine theta. Also, this last term becomes a minus cosine theta times a d theta ds, which really gives us just two of the same term here. Recalling that s is cosine theta, that's our transformation, we have 1 minus s squared times, I'll write this now as theta prime prime, where prime is a derivative with respect to the new independent variable s, minus 2s times our theta prime, plus mu minus m squared over 1 minus s squared times our theta is equal to 0. This is our new equation. Associated Legendre equation S will take values between -1 and 1. In cases that are rotationally symmetric, that implies your function phi is constant, which then implies that m is 0. If m equals 0, so that we are in the rotationally symmetric paradigm, the equation becomes 1 minus s squared theta prime prime minus 2s theta prime plus mu theta equals 0, which is somewhat simpler to solve, and it has its own special name. This is called a Legendre equation. For your information, the Legendre equation only has bounded solutions on the closed interval -1 to 1 if mu has the form n times n plus 1, where n is an element of the set of natural numbers or 0, the whole numbers. Since we're generally looking for bounded solutions, we will henceforth assume that mu has this form. The key then in solving these Dirichlet problems using spherical coordinates is to solving either a Legendre equation in the case of rotational symmetry, or the associated Legendre equation more generally. Now begins a rather long story, which is really part of a much larger story. Every second-order ordinary differential equation with 3 singular points, including infinity, can be transformed into the hypergeometric equation. The hypergeometric equation is the larger context, and so everything that we do here will be a special case of that larger context. So we begin the study of Legendre's equation which we will express as follows. The quantity 1 minus x squared times y double prime minus 2x y prime plus mu y equals 0. Here we'll assume that x takes values between -1 and 1. And it seems reasonable, since these coefficients are analytic functions, mu being a constant too, that y could be analytic. Which means that y has a power series representation having a positive radius of convergence. We can express it in the form, the sum as n goes from 0 to infinity, a sub n x to the n. From this, it follows that y prime is the sum as n goes from 1 to infinity of n times a n x to the n minus 1, and y double prime is the sum as n goes from 2 to infinity of n times n minus 1 an x to the n minus 2. Plugging all of this into Legendre's equation, we have 1 minus x squared times the sum as n goes from 2 to infinity n times n minus 1 an x to the n minus 2 minus 2x times the sum as n goes from 1 to infinity of n times an x to the n plus mu times the sum as n goes from 0 to infinity of an x to the n, and this was n minus 1, equals 0. There are a lot of nice outcomes when we simplify this. Multiplying by x here, we'll have an x to the power of n. That's nice. We don't need to re-index that sum. We'll distribute to each of these terms here. We have an x squared here, which will again give us an x to the n. Only term we have to re-index is the first one. I'll write it separately as the sum as n goes from 2 to infinity of n times n minus 1 an x to the n minus 2 minus the sum as n goes from 2 to infinity of n times n minus 1 an x to the n minus, we'll write this as the sum as n goes from 1 to infinity of 2n an x to the n plus the sum as n goes from 0 to infinity of mu an x to the n equals 0. This first sum is the only one that really needs to be re-indexed, and we need to have a new n hat be the old n minus 2, so that when we start with n equals 2, n hat will start at 0. So the sum that we replace this with will start at 0. N gets replaced by n hat plus 2, so we'll have n plus 2, n plus 1, a, n plus 2, x to the n. So these various sums start at different places. The only two that start at n equals 0 are the first and last. So when we plug n equals 0 here, we'll get 2a2 plus mu a naught is equal to 0. That's the n equals 0 case. When we deal with n equals 1, we'll have 3 terms show up. N equals 1 here gives us 3 times 2. This one doesn't have an n equals 1. This one does have an n equals 1. It'll be minus 2a1. And then this one has an n equals 1. It's plus mu a1 equals 0. That's the n equals 1 case. For n greater than or equal to 2, all 4 terms come in, and we'll have, this is the only one with an an plus 2. We'll have n plus 2, n plus 1, a n plus 2, plus all of the other terms have only an a sub n. We can factor the a sub n out, but we'll have a negative n times n plus 1 minus 2 n plus mu all times an equals 0. Where I've made an error, this should be n plus 2, and also this should be n minus 1. It follows then that an plus 2 will be, I guess when we move this over, we could change all of these signs. We can factor the n out. We'll have an n minus n and a plus 2n gives us n plus 1, and then minus mu when it goes to the other side. An divided by the coefficients here, n plus 2, n plus 1. Because this gives us an every other one principle, the odd coefficients will affect only odd coefficients down the line, and even coefficients will only affect even coefficients down the line. That implies then that we get even and odd solutions that I'll denote by y1 and y2. Just as important to note, mu is of the form r times r plus 1. If we want a bounded solution, r will have to take a value in the set of whole numbers, and if that's true, if mu is r times r plus 1, and r is equal to some whole number m, then we'll have m times m plus 1 here. So eventually, n is going to be equal to m, in which case the next coefficient is going to be 0. And if that coefficient is 0, it rolls back over to here. It means all future coefficients are 0. And that implies you get polynomials. If m is even, then the even function will be a polynomial. And if m is odd, then the odd function will be a polynomial. As you might have guessed, we're going to call these Legendre polynomials. But more generally, not all of these are going to be polynomials. They'll be functions. And so the solutions are going to be called Legendre functions. We are interested in convergence here. So we'll have an plus 2 x to the n plus 2 over an x to the n. This will give us adjacent terms with odd powers. This simplifies as an plus 2 over an times the absolute value of x squared. We'll now use this substitution to cancel out the an. Clearly, if we take the limit as n goes to infinity, we'll have x squared, which will converge provided that value is less than 1 by the ratio test. That means we get convergence on the open interval from -1 to 1. We'll have to check endpoints separately. You can note, however, that between -1 and 1, if a function is even, if it diverges at one endpoint, it will diverge at the other. And if a function is odd, if it diverges at one point, it also diverges at the other. Let's focus for the time being on Legendre polynomials. We may arbitrarily rescale the series so that the very last term, am, is 2m factorial over 2 to the m factorial squared. We will eventually show that this gives these Legendre polynomials evaluated at 1 to have a value of 1. It follows from our recursion relation that am minus 2 will in fact be negative m times m minus 1 over, now the denominator will factor, it will be n minus m plus 2 n plus m minus 1 all times a m. Notice I've kind of reversed the recursion formula. I'm solving for from the largest non-zero coefficient to the next largest coefficient. Continuing in this way, you may prove eventually by induction that am minus 2k is negative 1 to the k 2m minus 2k factorial over 2 to the m k factorial times m minus k factorial m minus 2k factorial, where you can see that if k is equal to 0, you'll get your 2m factorial, 2 to the m, 0 factorial is 1, m factorial, and m factorial. And so it is consistent with our normalization to begin with. We have then the Legendre polynomials of degree n, being given by Pn of x, is 1 over 2 to the n times the sum. As k goes from 0 to the greatest integer function of n divided by 2, the greatest integer function gives you the largest integer less than or equal to the given number. So for instance, if n is equal to 5, 5 divided by 2 is 2.5, the greatest integer would be 2. In other words, it chops the decimals off. We'll have negative 1 to the k times 2n minus 2k factorial x to the power of n minus 2k all over k factorial n minus k factorial n minus 2k factorial. These will give us one solution to our Legendre equation. The other solution will be denoted by Qn of x. And these will be the Legendre functions of the second kind. These will be polynomials, these will not be polynomials. The Legendre functions of the second kind will typically diverge at one of the endpoints, negative 1 or 1. Let's plot some of these functions. As you can see, I've plotted some even, these are the degrees, of these associated Legendre functions with 0 for the order. So that gives me Legendre polynomials. What you can see about these even polynomials, 0, 2, 4, and 6, they all begin at +1 and they end at +1. They're all even functions, so they're symmetric around their y-axis. They have all of their roots between negative 1 and 1. So the degree 0 is just a straight line, it has no roots, horizontal line. Degree 2 is this parabola right here, it has 2 roots. Degree 4 obviously then has 4 roots, 1, 2, 3, and 4, and then degree 6. Let's plot the odd powers then. And we should get odd functions. Oops. Should have made this a 3. And we'll make this a 7. As you can see, what we get now are degree 1, it's just y equals x. Degree 3 will be this cubic right here. All 3 roots between negative 1 and 1. Notice that in all cases, p of 1 is 1, where p of negative 1 for the odd will be negative 1, p of negative 1 for the even will obviously then be positive 1. What do these Legendre functions look like when we have a non-whole number in this spot? You can see now a little bit of what's going on. I need to change the number of points. So you can get a better idea that this function diverges at negative 1. It will converge at 1 to some finite value. But at negative 1, we have this function, this infinite series, diverging.
Same thing if I have 1.4. What if I try something like 2.4? You can see it diverges now at this left endpoint still. You can see here I'm asking my computer to solve as a differential equation, dsolve, 1 minus x squared y double prime, that's how you do two derivatives, minus 2x times y prime plus 6y equals 0. This is a Legendre equation where mu equals 6, which is 3 times 2. And the solution it gives me right off the bat has this even polynomial. And I'd like to look at these Legendre polynomials if I have something like 3/4. At 3/4, you can see that I get a function that is neither even nor odd, and that has a singularity at x equals -1.
We can make a few observations. First, if n is even, Pn is an even function. N is odd, Pn is odd. Second, all of these polynomials, if n is a whole number, evaluated at 1, give you 1. At -1, it gives you -1 to the n. And that's for all n element of the set of whole numbers. A third observation is that provided n is a whole number, these Legendre polynomials are bounded by 1. And that's true for all x between -1 and 1. A fourth observation is that Pn of x for n in the set of whole numbers has n zeros or roots in the interval from -1 to 1. So all of its roots are within that interval. Finally, all relative extrema of Pn of x, and of course in the whole numbers, lie between -1 and 1. We'll talk about Legendre series expansions that allow us to solve the rotationally symmetric problems, and then we will turn to the associated Legendre equation with its associated Legendre function associated with the generalization of our Legendre series expansions. That will give us the ability to completely solve these Dirichlet problems in spherical coordinates. From there, we'll look at the Helmholtz equation and solve the associated eigenvalue problems there. We'll look at Poisson's equation. We'll look at the non-steady state heat equation as well as the wave equation. So, we have a set of orthogonal functions. The next obvious step is to take those functions and use them to pick apart functions by some kind of Fourier series. That's the plan. And the theorem goes like this. If f is a piecewise smooth function on the closed interval from -1 to 1, then f is some kind of a sum as n goes from 0 to infinity of an times Pn. Here, an 2n plus 1 over 2 times the integral from negative 1 to 1 of f of x times Pn of x dx. You can see the inner product together with the appropriate normalization. Continuing the statement of the theorem, the series converges pointwise for each x in the open interval from negative 1 to 1 at which f is continuous. So wherever the function is continuous, we get pointwise convergence on the interval. What happens at a point of discontinuity? At those points, the series converges to the average of the left and right limits. If f has a jump discontinuity at some x, then the series converges to 1/2 f of x minus plus f of x plus. So the average of the limits from the left and the right at each point where we have a jump discontinuity, just like the regular Fourier series. Of course, we need to show that our collection of Legendre polynomials is orthogonal. Without that, we got nothing. For this purpose, we use the following theorem. Rodriguez's formula. It says Pn of x is 1 over 2 to the n factorial times the nth order derivative of x squared minus 1 to the power of n. In our proof, we ask that you recall that we have a formula for Pn of x. It's 1 over 2 to the n, the sum, as k goes from 0 to the greatest integer function of half n, negative 1 to the k, 2n minus 2k factorial x to the n minus 2k over k factorial, n minus k factorial, n minus 2k factorial. Just taking a look at the degree, if we were to take a number between n over 2 greatest integer and n, then the nth order derivative of x to the 2n minus 2k will have to be 0. If you subtract off enough, the power will be so low that the nth order derivative will end up being 0. You can see that if k is bigger than n over 2, this will be bigger than n. You'll be subtracting more than n off of the 2n, so the power here will be less than n, which means the derivative will have to be 0. Alternatively, if we choose the k value on this side, between 0 and the greatest integer function of n over 2, then the nth order derivative of x to the power of 2n minus 2k will be n degrees lower. It'll have to be 2n minus 2k factorial, but we don't get all of those factors, so we'll have to subtract off the factors that we don't get, n minus 2k factorial, times x to the n minus 2k. It follows then that Pn of x will be 1 over 2 to the n. My goal was to have an n factorial here. I'll have to balance that off by putting an n factorial on each term in the sum. And we may as well go all the way to n, since the latter half will be truncated out anyway, since we've already shown that those derivatives give you 0. We'll have negative 1 to the n, our counterbalancing n factorial. We still have the k factorial and n minus k factorial down here. And it's the nth order derivative of x to the 2n minus 2k. We'll next pull the derivative out of the sum. We'll have this negative 1 to the n, the binomial coefficient n choose k, which is right here, times x squared, factoring the 2 out, to the power of n minus k. This part we can apply the binomial theorem to write as x squared minus 1 to the power of n. And so by the binomial theorem, we have Pn of x is 1 over 2 to the n factorial times the nth order derivative of x squared minus 1 to the power of n. We will also need the Benet's recurrence relation. And it's easy to remember if you put it in the right form, but it works for n that are element of the set of natural numbers. We'll have n plus 1 times Pn plus 1 of x plus n times Pn minus 1 of x. And if you add n plus 1 and n, you get 2n plus 1. We'll have an x and a Pn of x. Notice this factor of x right here. In the proof, we'll set u to be x squared plus 1. Minus 1, and instead of writing the derivative with respect to x, we'll just use a d. So notice that Rodriguez's formula can be expressed as Pn of x is 1 over 2 to the n factorial times the nth order derivative of u to the n. So we're going to look at, to begin with, just a second order derivative of u to the n plus 1. And you can see that that's going to be one derivative after another. One derivative of u to the n plus 1 will bring the power down, subtract 1 from the power, and multiply by the derivative of the inside, which is 2x, using the chain rule. So a 2 and an n plus 1 can come out of this. What's left over is the derivative of x times u to the n. Well, the derivative of x is 1, so we'll have u to the n. And derivative of u to the n times x, we'll have that x left over, times n u to the n minus 1 times another 2x. Notice we get an x squared here. And x squared, since u is x squared minus 1, x squared is u plus 1. So we can replace this x squared with u plus 1. We have then that d squared un plus 1 we have this 2, n plus 1. When we distribute the 2n u to the n minus 1 through here, we'll have this u to the n plus 2n times, we'll have u to the n plus u to the n minus 1. We can combine like terms. We'll have 2n plus 1 times u to the n plus 2n times u to the n minus 1. We'll now look at dn plus 1, u n plus 1, and the way we'll do that is we'll split off two derivatives first and use the formula that we have just derived. So we'll end up with 2 times the quantity n plus 1 times 2n plus 1. We'll have n minus 1 derivatives applied to this u to the n plus 2n n minus 1 derivative applied to u to the n minus 1. We'll now recall that by Rodriguez's formula, Pn plus 1 of x is 1 over 2 to the n plus 1 factorial times the n plus first derivative of u to the n plus 1. And here we get to apply the formula that we've just derived. Notice that a 2 can cancel, leaving it 1 over 2 to the n. N plus 1 will cancel, leaving an n factorial. And you can see that on this next term, we'll have 2n plus 1 dn minus 1 un plus 2n dn minus 1 un minus 1. You can see that if we were to distribute the leading coefficient out here onto the second term in the parentheses, a 2 and an n will cancel, giving you 2 to the n minus 1 factorial. We end up with a p n minus 1 over here after distributing, because the 2n will cancel, leaving you everything you need by Rodriguez's formula to come up with Pn minus 1. And so this term straight up becomes Pn minus 1 of x. On the first term, we'll still have 2n plus 1, 2 to the n factorial, dn minus 1 times u to the n. So this is one representation of Pn plus 1 of x. But we can use another. So we have Pn plus 1 of x is Pn minus 1 of x plus 2n plus 1 over 2 to the n factorial dn minus 1 u to the n. But hold on, there's another way to view this. By Rodriguez's formula, we can split off one derivative and then apply the chain rule. We'll have n plus 1 u to the n, but we have a factor of 2x that comes from the derivative of u with respect to x. The n plus 1 here can cancel, leaving you with an n factorial, just as the 2 can cancel, leaving with 2 to the power of n. But now we have kind of a product rule with what's left. Well, it is a little bit complicated in the sense that you can't just do the usual product rule of the two factors with nth order derivatives. But I think you might be able to see that eventually you'll get the nth order derivative of u to the n times an x. And then there are going to be n different terms where you have the derivative of x one time. Other terms where the derivative of x is higher than the first order will give you 0. So you'll have n. So you'll have n terms where you do the derivative of x one time and n minus 1 derivatives of u to the n. When you distribute now, you can see that you'll have, by Rodriguez's formula again, x Pn of x plus n over 2 to the n factorial dn minus 1 u to the n. Both representations have a term involving dn minus 1 u to the n. And so we're going to play those off against each other and try to eliminate those terms. We'll have to multiply each of these equations by what's missing on the other equation. So we'll have 2n plus 1 here, 2n plus 1 here, 2n plus 1, and we'll multiply by n, n, and n. Now the last terms are identical, so we can just subtract. Subtracting these two, we'll have n plus 1 times Pn plus 1 of x. We'll have equals 2n plus 1 times x, Pn of x, minus n, Pn minus 1 of x. Moving this term to the other side, the proof is done. The next theorem is kind of what we've been working for. If you take the inner product of two distinct Legendre polynomials or Legendre functions, you get 0. What's the correct normalization factor? You get 2 over 2n plus 1. For the proof of part 1, suppose m and n are distinct, and we're going to write the Legendre equation in a special form. You can see we almost have a product rule going on here. So let's unravel that. In this form. Recall that mu must be r times r plus 1. So if r is m, it's going to be m. If r is n, it's going to be n. It follows then that we have 1 minus x squared Pm prime is minus m times m plus 1 times Pm. And also 1 minus x squared Pn prime is minus n times n plus 1 Pn. For simplicity's sake, we might say minus mu m Pm and minus mu n Pn. Now we're going to look at a special combination here. And if you distribute to each of these, we can combine in a special way to rewrite this as minus, this ends up being 1 minus x squared Pm prime Pn, and then plus 1 minus x squared Pm, this is an m here, Pn over here, prime prime PM. And you can check that that is equal to the ordinary derivative of 1 minus x squared times the quantity PM Pn prime minus Pm prime Pn. You can see that by the product rule, if you distribute and reassociate these in certain ways, this times the Pn prime term, the derivative there would give you this term here. Alternatively, if you just take the derivative of the Pm, you'll get Pm prime times this, and that would be 1 minus x squared times Pm prime Pn prime. Looking at the other term, making the association here, you'll get P 1 minus x squared Pm prime quantity prime times Pn. That's this term here. But on the other term, it's just going to be the 1 minus x squared times Pm prime Pn prime, which will cancel the same term that we had from over here. So all terms are accounted for. The interesting trick then is to take your terms and integrate from -1 to 1. On the right-hand side, you'll have the integral of a derivative. So the antiderivative will be what's inside, and you'll be evaluating that at the two endpoints. But when you plug in 1 for x, you get 0 on that term, and the same thing when you plug in -1. So, the whole thing 0. On the left-hand side, we have the inner product of Pm with Pn multiplied by this factor. This factor is not 0 because m and n are distinct, and therefore we get the inner product as 0. We only have to prove the normalization factor. So for part 2, we'll start with Benet's relation. We have this, but the formula is also true if we replace n by n minus 1. That'll give us n Pn of x plus n minus 1 Pn minus 2 of x. If we replace n by n minus 1, we'll have 2n minus 1 x Pn minus 1 of x. To simplify these, we'll multiply the first equation by Pn minus 1 of x, and the second equation by Pn of x. We have then n plus 1, Pn plus 1, Pn minus 1, I'll suppress the functional dependence on x, plus n times p squared, n minus 1, equals 2n plus 1 x Pn minus 1, and we'll also have n Pn squared. Let's see, what do we want to do with this term? Plus n minus 1 Pn minus 2 equals 2n minus 1 x Pn minus 1. If we take this first equation and integrate everything in sight from -1 to 1, because these are distinct, the integral in this first term here will be 0. And on the second term, the 2n plus 1 can come out front. We'll have x Pn minus 1. On the second equation, when we integrate, the second term on the left-hand side will go away, and we'll end up with n times the integral from negative 1 to 1 pn squared of x dx is 2n minus 1, the integral from negative 1 to 1 x pn minus 1 dx. Now the right-hand sides on both of these equations are very similar, except for one has a 2n plus 1 and the other one has a 2n minus 1. We'll eliminate this term by multiplying the first equation by 2n minus 1 and the second equation by 2n plus 1. We can cancel the n's off after that process. We'll simply solve for this factor here, integral from negative 1 to 1 pn squared of x is 2n minus 1 over 2n plus 1, integral from negative 1 to 1, pn minus 1 squared of x dx, and now the rest follows by induction. But you need to use the fact that, first of all, p naught of x is identically 1, which implies that the integral from negative 1 to 1 of p naught squared of x is 2. Remember the formula that we're trying to prove is 2 over 2n plus 1. You can see that if you put a 0 here, you'll get 2. So the formula is true when n equals 0. I'll let you fill in the rest of the proof by induction, and we'll call the proof over at this point. As an example, suppose our function is u, and it's defined so that it's 0 for x less than 0 and 1 for x greater than 0. So it's just a simple unit step function like this. We are operating between negative 1 and 1 here. So the area that we're going to capture when we integrate this function by itself, or even that function squared, will be 1. Let's do the inner product of u with p naught. It's the integral from negative 1 to 1 of our function u times p naught, but p naught is identically 1. And so we just get the area under this function, which is 1. How about the inner product of u with p1? That's the integral from negative 1 to 1 of our, we may as well go from 0 to 1 since we have a step function. We'll replace that by 1. What we need is a formula for p1. Well, we can apply Rodriguez's formula. That's 1 over 2 to the 1 factorial, the first order derivative, and it's of x squared minus 1. As you can see, the derivative is going to be 2x, which we can cancel, or just getting an x. Y equals x will give you an integral from 0 to 1 of 1/2. Let's try the inner product of u with p2. Again, we only have to integrate from 0 to 1 because of the step function nature. So we're integrating p2, which is 1 over 2 squared 2 factorial times the second order derivative of x squared minus 1 squared dx. Well, let's see, x squared minus 1 squared is x to the fourth minus 2x squared plus 1. If we do one derivative, that's going to be what? 4x cubed minus 4x, and then one more derivative. We have a 1/8 here. One more derivative gives you what? 12x squared minus 4. And we're integrating from 0 to 1. So that's going to be 1/8 times, I have x cubed over 3. 3 goes into there 4 times. minus 4x. And so when we plug in 1, we get 0. When we plug in 0, we get 0. And so the inner product of u with p2 is 0. I'll record that over here. And now let's do the inner product of u with p3. The inner product of u with p3 is the integral from 0 to 1 of the third order derivative of x squared minus 1 cubed. So let's we can cube this. We'll have minus 3x to the fourth plus 3x squared minus 1. So that's what goes here. The first derivative is going to be 6x to the fifth minus 12x cubed plus 6x. That's the first derivative. The second derivative is going to be what? 30x to the fourth minus 36x squared plus 6. And then we need the third derivative. That's going to be what? 120x cubed minus 72x. So, oops, I forgot my 1 over 2 to the power 3 times 3 factorial. So we're multiplying by 8 here and 6 here. So it's 1 over 48. Some of that can already be used to reduce the coefficients. So for instance, 12 goes into here 4 times, into here 6 times, and into here 10 times. I guess I should have put 24 into each of those. So let's see, we'll cancel one more 2. I have a coefficient of 3 here and a coefficient of 5 here. So we'll have 5x to the fourth over 4. This is all times 1/2 minus 3x squared over 2. Plugging in 1, we have 1/2 times 5/4 minus 3/2. That's minus 6/4. So we have a negative 1/4 here times 1/2, we get negative 1/8. Let's try to put all this together and make an approximation to the unit step function by these projections. The last inner product we calculated was the inner product of u with p3, which was negative 1/8. Now remember, our formula added these inner products, but they were normalized. So we have to divide these by the inner product of p0 with p0 or p1 with p1. And those were 2 over 2n plus 1. You'll remember, if you take the inner product of pn with pn, you get 2 over 2n plus 1, which was proved by induction. So we need to divide by those. Since we're dividing by those, we'll end up with terms that look like the inner product of u with p0. Let's see, we'll end up with terms that look like the inner product of u with pn times 2n plus 1 over 2 to take care of the division by the inner product of pn with pn. So this u function will be approximately equal to, we'll have 1, and when n is 0, this will be a half. So we'll have 1/2. This next inner product, u with p1, ended up being 1/2. So it's going to be plus 1/2 times, n is 1 this case, so it's going to be times 3/2 times p1 itself. And recall that p1 was equal to x. The term involving p2 was 0, so the next term that's non-zero will be this negative 1/8. This is the n equals 3 case, so 6 plus 1 is 7. We'll have 7/2. And just in case you don't remember, over 2 minus 3x over 2 was our Legendre polynomial. So putting this all together, we'll have a cubic polynomial approximation to the step function. That's minus 35x cubed plus 45x plus 16. How good is that approximation? It doesn't end up being very good. It does something like this. In order to get a better approximation, all we need to do is truncate this series a little farther out. Let's try some of that on the computer.
As you can see, I've already begun the computation here. I've assigned big N to be 3. That's how big degree terms we're going to get out of this. And I'm assigning my coefficients here, a sub n, by evaluating as a floating point number the integral of my Legendre P polynomials with n. N goes from 0 to the assigned number 3 over here. After we evaluate the integral, we multiply by the normalizing factor of 2n plus 1 over 2. So these are the coefficients of the Legendre series that we're going to construct. We'll have the sum of these coefficients times the corresponding Legendre polynomials. These are the coefficients that you get from the Fourier series formulas. And so we've defined this function, and now we have a graph. We can scroll down and see the graph, and voila, there it is. It seems that this is a rather poor rendition of the step function. Maybe we can do better by changing n to something bigger, like say 10. And you can see this is a lot better variant on the unit step function. But still, it almost looks like you can see the Gibbs phenomenon forming there. Let me change this a little bit. I'll change some things from indicating you should show it to not show it. Save a little space. Let's change this to 20, truncating the series much farther back. And you can see that we are getting a pretty good rendition of the unit step function and definitely overshooting at the 1 here. You would still exhibit the Gibbs phenomenon, even using these Legendre polynomials. 100 just took too long. Let's try 30. Let's not be quite so brash. Yeah, it looks a little chunky. We may need to add more points. Yeah, you can see this going crazy to the left of -1. I think that's an artifact of graphing. N equals 40. Away from discontinuities, -1, 0, and 1, we should have away from discontinuities, we should have a uniform convergence to the unit step function. And it is getting pretty uniformly close. At the discontinuities, we have the Gibbs phenomenon. So we do not get uniform convergence there. So you can see then that we have a complete solution to the problem of say, heat flow in a ball or steady state heat in a ball provided we have rotational symmetry. We still haven't discussed the more general case, and to do that, we're going to have to find what is called the associated Legendre polynomials, or Legendre functions. And that will then give us a complete solution, but that's one step beyond this.